Section 15.2, double integrals over general regions. So in this last section, I've only been looking at integration where I'm integrating over a rectangle. So we're going to do the same thing, but now we're going to integrate over any sort of general region. It has measure more than 0. Okay, so let R be a rectangle such that D is a subset of R. Then I'll define F, capital F, of XY as equaling F of XY if XY is in D, and 0 if XY is not in D. I'll then define the double integral over this general region D of F of XY to equal the double integral over the rectangle, which we defined previously, over this newly defined function, capital F of XY. So we can now define double integrals, and it really doesn't matter the region that we're integrating over. It's the same sort of idea that we just had in the previous section. So we can think of these different ways of integration in terms of different types of regions. One where I first integrate with respect to, let's say, X, and then, I guess I'll integrate first with respect to Y, and then integrate with respect to X, or vice versa, when I first integrate with respect to X and then integrate with respect to Y. So I'll call this a region of type 1 if I can write it as follows. So if D can be written as let X go between two fixed values, A and B, and let Y be bounded by two functions, G of 1 of X and G of 2 of X. Then I can write the double integral as the integral from A to B when integrating with respect to dx, and the integral from G1 to G2 of X when I integrate with respect to Y. So notice, I'm integrating my dy, my function with respect to Y. It could be that my limits of integration involve X. Then when I integrate with respect to X, if this is the last integration I'm doing, I only want limits of integration that are numbers, no variable in it. If instead I have a region of type 2, say D can be written as Y is in between two fixed numbers, C and D, whereas X is in between these two functions, H1 and H2 of Y, then I can integrate as follows. So notice that my first integration with respect to X will involve limits of integration that involve Y, but when I do the last integration, my limits of integration do not depend on any variable. There'll be some fixed numbers, say C and D. Okay? And so what you notice is that sometimes when you do a limit of integration, one of these integrations may be easier. If the integration is easier, then you do it that way. If it's not easy, then you try the other limit of integration. And so how do you know which one a priori will be easier? You don't. You try it. If it's easy, it works. And if it's not easy, then you try the other way. Of course, you have to be sure that Fubini is applicable. Well, no, what I would say is you try one way. If you're able to finish it, then you're happy. If all of a sudden you get stuck, try the other way. So I would say don't try both ways. Try one way. If it works, then you're happy. If it doesn't work, then you try the other way. So I myself never try both ways. I just pick one of them, see if it works. If it works, I'm happy. If it doesn't work, then I just say, okay, well, I'll start all over again, but I'll do it the other way around. Okay? Oh, no. Well, all I'll say is that in this book, so long as Fubini, remember, Fubini's theorem says that the limits of integration, either limits of integration work and are equal. So long as Fubini holds, then everything is okay. They both give you the same answer. Okay, so so the limits of integration, you can switch the order so long as Fubini's theorem holds. In this book, all examples, yeah, I think so. I think all examples, Fubini's theorem works. Okay, I gave you one where it didn't, but that's, because Fubini, the properties of Fubini's didn't the assumptions didn't hold, so you wouldn't expect that necessarily Fubini's theorem would be true for it. Okay, so properties of double integrals, linearity. Just like in the one variable case, if you have two functions, you want to integrate them, you just take the integral of each and add them up. If you have a constant times the integral times a function, and you integrate that the same as that constant times the integral of the function. And so the double integral of f plus g is the same as the double integral of f plus the double integral of g. The double integral of a times f is the same as, well, bringing the a outside the integral, a times the double integral of f. So combining these, the sum formula and the constant formula, we have that the integration is what's called a linear transformation. Just like what we talked about, the derivative was a linear transformation. The integral is also a linear transformation. And so the double integral of AF plus BG is just equal to A times the double integral of F plus B times the double integral of G. Order. So again, we have the same property that we had for the one variable case. If f is greater than or equal to 0 on some region D, then the double integral over D of f is greater than or equal to 0. And so just like in the one variable case, if you're above the x-axis, then the integral gives you some area, some positive area or non-negative area. If, here just define f minus, if I look at f minus g in this first case in using linearity, I get the second case. If f is greater than or equal to g on D, then the double integral of f over D is greater than or equal to the double integral of G over D. Disjoint partitions. Again, this is the same as the integral from in the one variable case, the integral from a to b is the same as the integral from a to c plus the integral from c to b. Let D equal D1 union D2, and let D1 intersect D2 be the empty set. Then the double integral of f over d is equal to the double integral of f over d1 plus the double integral of f over d2. Similarly, if I partition my region into a finite or even infinite, well, finite number of disjoint sets, then the above holds also. So let D equal the union of dj from j equaling 1 to n, and let the intersection of dj from j equaling 1 to n be the empty set. Then the double integral of f over d is equal to the sum for j equaling 1 to n of the double integral of f over each of these dj's, which were disjoint. It's very important they're disjoint. Otherwise, this is not going to be true. We define the area of some region D as being the double integral of 1 over the region D. Bounded. Let F be between little m and big M for every x, y in D. Then M times the area of D is less than or equal to the double integral of F over the region D, which is less than or equal to capital M times the area of D. The mean value, or the average value, there exists point x0, y0 in D such that the double integral of f over d is equal to f evaluated at x0, y0 times the area of d. Or in general, let g be greater than 0 for all x, y in D. Then there exists x0, y0 in D such that the double integral of f times g over d is equal to f at x0, y0 times the double integral of g over d. Oops. Let's evaluate. Let's do problem number 4. Okay. On page 1048, in exercises 1 through 6, evaluate the integrated integral. So the integral from 0 to pi over 2 with respect to x, the integral from 0 to x with respect to y. So let's first integrate this with respect to y. So this is the integral from 0 to pi over 2. So let's integrate this first with respect to y. So y is a variable, but x is a constant. So the integral of a constant times sine of y is, well, minus that constant times the cosine of y. And let's evaluate this between y equals 0 and y equal x. So notice here that my outer integration, my outmost integration has limits of integration being constants. Whereas as I go inside, my limits of integration can involve previous integrations of the variables of the latter integrations. So that what happens is once you substitute in these values, when you integrate further, you'll get rid of those variables. And so in general, the innermost variables can contain any of the outermost variables until, of course, you don't have any more outermost variables, in which case they must be constants, which they are here. Okay, so let's integrate this. So this is integral from 0 to pi over 2. I'm going to substitute for y, x, for y, 0. And so cosine of 0 is just 1. That becomes an x. So now let's integrate this. And so the integral of x cosine x, well, I can do that several ways. I guess the way that I'm going to do that is integrate by parts. And so let's integrate here by parts. Actually, let's do this. Let's do the whole thing integration by parts. Okay, so why don't I do that? So let's integrate this by parts. So I'm going to integrate by parts here. So the integral of u dv is equal to uv minus integral of v du. Let's do, oops, obviously let's add another page. I'll need it a little bit more. Okay, so, and maybe what I'll do is over here, I'll say what du and dv are. And so v u dv. And then du dv, du and v. So I'm going to integrate by parts. Okay. So maybe what I'll do is I'll factor out the x here. And so I'll just let this be x. And then dv be everything else. So if I factor out that, there'll be a negative cosine plus 1. So how about 1 minus cosine x dx. And so if I integrate that, I'll just have x plus sine minus sine. Okay. Derivative of sine is cosine. Okay. So this is equal to x okay. And so this is equal to x minus sine x for x between 0 and pi over 2 minus integral between 0 and pi over 2 of x minus of v du. So it's x minus sine x dx. So this is equal to, plug in pi over 2. So you get a pi over 2 times pi over 2 minus the sine of pi over 2, which is 1. Plug it in 0, you get 0. Minus, well, let's integrate this. So this is going to be a 1/2 x squared plus cosine x between 0 and pi over 2. So this is equal to pi squared over 4 plus minus pi over 2 minus, plug in that, they'll give you 1/2 pi squared over 4 pi over 2 is cosine pi over 2 is 0. Minus, plug in 0, you get 0 and 1. Okay. So this is equal to pi 2 pi squared over 8 minus pi squared over 8 is pi squared over 8 minus pi over 2 plus 1. And that is your answer. Okay. Let me do number 8. 7 through 10, evaluate the double integral. So I have here the double integral over the region D of 2x plus y, where D is equal to the such that y is between 1 and 2 and x is between y minus 1 and 1. Well, notice that this quantity is a number. So if I try to evaluate this, now someone was asking, well, how do I know if I put x or y first? Well, it doesn't matter so long as everything is done properly. So let's say that we did dy dx. So y is between 1 and 2, and x is between 1 and y minus 1. Well, if I integrated this, I would just get some sort of function in terms of x, and there'd be no y. And then when I integrated this, since I'm evaluating at y minus 1, I get some function y. But of course, this is impossible because you want it to be some number. So we can't do that. So we know that this is going to equal. So on the outside, it'll be numbers. On the inside, so this is my dy. On the inside, we're going to, I'm sorry, that's my dy. On the inside, I'm going to integrate with respect to x. Now, these endpoints here can be any function of a variable on the outside. And so these limits here can be variables of y. That's fine. They cannot be variables of x or anything else, but they can be a variable of y. This, since it's the outermost, must be a number. It can't be a function of anything else because there's no variables here. And so this is the integral from y minus 1 to 1. Oh, I guess I wrote it wrong the first time I wrote it, but it doesn't really matter. So now let's integrate this. So first, I'm going to treat y as a constant and integrate variable. And so this is just going to be, well, integral of 2x is just x squared. Integral of the constant y is just xy. And I'm going to evaluate between x equaling y minus 1 and x equaling 1. And then I'll integrate that, whatever I get. And so this is equal to, well, let's plug in 1. So the integral from 1 to 2. Plug in 1 for x, I get 1 plus y minus, plug in y minus 1 for x, so get y minus 1 squared plus y minus 1 times y. Okay, so let's simplify this. So this is equal to, I'm going to go from 1 to 2 of 1 plus y minus y squared minus 2y plus 1 plus y squared minus y. dy. So this is equal to the integral from 1 to 2. I have a y squared and y squared, so that's a minus 2y squared. No, I could have just integrated that without doing that. It doesn't really matter. So this is equal to a minus 2y squared. This is minus 3y, so it's a plus 3y, so plus 4y. And then the ones cancel. dy. Okay, and so let's integrate this. So this is equal to minus 2/3 y cubed plus 2y squared evaluated between 1 and 2. So this is equal to minus 2/3 times 2 cubed plus 2 times 2 squared minus plug in 1, negative 2/3 plus 2. So this is negative 16/3 plus 8 plus 2/3 minus 2. So this is going to equal 6 minus 14/3. So 18/3 minus 14/3 is 4/3. So that's 6, 18, 2, 4. Yes, that is correct. Okay, so we get that is equal to 4/3. Problem number 23 through 32, find the volume of the given solid. So problem number 24. Under the surface, Z equaling 1 plus x squared y squared, and above the region, enclosed by x equal y squared and x equal 4. And so let me draw the region here, just region, not the actual volume of the region. And so if I'll write it sort of strangely, since this is written as x as a function of y, rather than drawing it this way, I'll draw it where x is up here and y is down here. And so this is the graph of x equal y squared. And here's a line x equal 4. And so it's this region here is my region that I'm going to be find the volume of the surface above that region here. So let's do this. So I have, y goes from minus 2 to plus 2, okay? And x here goes from, y squared to 4. And so the volume is just going to be the integral from minus 2 to 2, integral from y squared to 4 of z, which is 1 plus x squared y squared dx dy. And so in this case, it was easy to figure out what x is in terms of y. So that's why I did dx first and then dy. You could have done it the other way around, but then you'd have to, this would be like a square root plus a square root, and this would be a minus the square root, and it'd just be a little messier, that's all. This is the integral from minus 2 to 2. I'm integrating with respect to x, so it's x plus 1/3 x cubed y squared between x equaling y squared and x equaling 4. Okay, let me get another page. We don't need the whole page, I don't think. So this is equal to integral from minus 2 to 2 plug in y squared. So this is y squared plus 1/3. Y squared to the third, maybe I'll just write it this way, times y squared minus plug in. Okay, so plug in 4. So I'm going to get here 4. So here. So I'm going to get 4 plus 1/3. Okay, 1/3 times 4 cubed y squared dy. So this is equal to integral from -2 to 2 of y squared plus 1/3 y to the 6, 8, y to the 8 minus 4 minus 64 over 3 y squared so this is equal to wait, why did I do it backwards? I don't know. Why did I do it backwards? I don't know. So this is equal to the integral from -2 to 2 of plugging in 4. That'd be a 4 plus 1/3 4 cubed y squared minus plugging in y squared plus 1/3 y squared cubed y squared dy. So this is equal to integral from -2 to 2 of 4 plus 64 over 3y squared minus y squared. Those will combine, minus 1/3 y to the 8 dy. So this is the integral from -2 to 2 of 4 plus 61 over 3 y squared minus 1/3 y to the 8 dy. So now let's integrate this. And so I get 4y plus 61 over 9 y cubed minus 1 over 27 y to the 9 between -2 and 2. Oh, and that's odd, so that's good. So I get that this is equal to 4 times 2, 8, plus 61 over 9 times 8. So 61 times 8 is 488 over 9. Oh boy, 10 to the 9th is 512, right? Over 27 minus, well, I'll put in another minus here. Minus 8 gives me a plus 8. And subtracting a negative 488 over 9 gives me a plus 488 over 9. And subtracting a negative is a plus. And at -2 to 9, that gives you a negative 512 over 27. Okay. And so that gives you 16. Oh, we got to multiply by 27. Okay, so 16 plus 8, 976 over 9 minus 1,024 over 27. So this is equal to 2,336 over 27. And that's your answer. Okay. In problem 61 through 62, find the average value of f over the region D. Oh, there it is. In problem 62, f of x is equal to f of xy is equal to x sine y. D here is enclosed by the curves y equals 0, y equal x squared, and x equal 1. So let me draw that. Yes. Okay, sorry, I was just checking if it was 2,336 over 27. Okay, so let's do this. So my region D is enclosed by y equals 0. So here's y equals 0. X equal 1. So I'm drawing this the normal way. So x and y are written this way. So x is equal to 1 and y equal x squared. So it's just this little region. Okay, so let's figure out what this is. So let's integrate first with respect to here, with respect to y, then with respect to x. Okay, so the average value f will equal, well, let's see, this is going to be the double integral. So first x goes from 0 to 1, and then y goes from 0 to x squared. And I'm going to be integrating my function x sine y. And then this is dy dx over, well, the same thing, integral from 0 to 1, 0 to x squared. In this case, 1 dy dx. Question. Does it matter which one you do first? No, you'd have to, let's say, again, it could be that one way is easier than the other. So in this case, you have this region. It's not going to be that different. So this, in this case, y goes from, so I'll do it both ways. Sometimes it's easier one way as compared to the other, because everything, y is written as a function of x. Okay, so now, so this is 1 here. And so since y equal x squared, this is 1. Okay, so y goes between 0 and 1. So I could do, I'm going to erase this, by the way, but it goes, y would go between 0 and 1. But now, what is x? So x here in this slice, so that's x equal 1 here. But here, x is equal to, actually it's a positive square root of y. Y is positive, so that's fine. So it goes between 1 and the square root of y. X sine y dx dy. Okay. And then the other integral is however you want to write it. I've written it either way, but maybe I'll do it as, that's a y. Dx dy. Now, to integrate this, you integrate respect to x. So once you've integrated this, you're going to be integrating something of the form, oh, wait, that's a square. Oh. So you're going to have to do an integration by parts. This is sine y, one of the terms, and the other one will be a sine y, which is easy to integrate. So you'd have to do an integration by parts. It's not so bad. It's doable. So it's a doable integration. Let's see if this is doable. I think this might be easier to integrate, I think. Okay, so let's do this calculation. Oops. So let's do the integral from 0 to 1. Oh, I don't know. Let's do this one. And from 0 to x squared. Let's do the denominator first. This will be a particularly easy integral. So integral of 0 to 1 of y between y equals 0, y equal x squared. And so this is just equal to the integral from 0 to 1 of y squared minus 0, so that's just y squared, x squared. Why did I write y squared? That's just x squared. So let's integrate this. So this is just 1/3 x cubed between 0 and 1. So you're going to get 1/3 minus 0 is 1/3. So that's an easy integration. Let's do the next integration. From 0 to 1 is 0 to x squared of, what was it, x sine y. And this was a dy dx. Okay, so let's do that integration. So this is going to be the integral between 0 and 1. The integral of sine is minus cosine, so minus x cosine y. And I'm evaluating this between y equals 0, y equals x squared. Okay. And so this is equal to the integral from 0 to 1, plug in x squared, so it's a minus x cosine x squared, which makes that an easier integration. You don't have to integrate by parts or anything. And then cosine of 0 is 1, so minus a negative, oops, which makes that a positive x dx. Okay, so let's integrate this. So this is, the integral is minus 1/2 sine x squared. Okay, plus integral of x is 1/2 x squared. Okay, that's good. And I'm going to, that's an x squared. I'm going to evaluate this between 0 and 1. And so let's plug in 1. So I get the sine of 1 plus 1/2. If you plug in 0, you get 0. So now let's find the average value. So the average value was equal to 1/2 minus, and let's factor out the 1/2, divided by, I think it was 3/2, if I remember correctly. No, not 3/2, it was 1/3. Okay, let's get back down, if I can. Just down, all I'm asking. Oh, scroll down. Come on, move. Okay, so dividing by 1/3. And so I get that this is equal to, so this is equal to 3/2. Okay, come on. 3/2 times 1 minus sine of 1. And that is your answer.